In this video, we are going to look at methods for finding eigenvectors of a matrix A, starting by sort of deriving the method, and then we'll look at some examples of finding eigenvectors. So our goal is going to be given a matrix A, to find all vectors v and all scalars lambda so that AV is equal to lambda v, where v is non-zero. The wrinkle with this is that the only information we know is the matrix A. We don't know the number lambda, and we don't know the vector v. Okay. So we're going to solve this with just normal algebra methods, which is what we would want to do in a linear algebra class. It gets a little bit funny at some places. Don't worry, we'll get through it. It's no problem. So we're trying to solve AV equals lambda v. Our first step, just like in your Algebra 2 class, is to rewrite it so that all of the v's are on the same side. AV minus lambda v is going to be equal to the 0 vector. You can see here now we have v in both terms on the left-hand side. The one sort of funny thing that makes it hard to go forward is that in this first term we have a matrix times v, and in the second term we have a scalar times v. So what we're going to do, which is going to feel slightly odd, is we're going to rewrite this scalar times v so that it has a similar form as a matrix times v. So we're going to rewrite lambda v in the completely identical way, lambda times the identity times v. These are equal vectors, but when we rewrite this way, I have a matrix lambda I, so I can more easily consolidate it with the matrix A. Okay. So I'm going to rewrite my expression as A times V minus lambda I times V is equal to 0. I now have my vector V on the right in both terms, and I also have matrices A and negative lambda I on the left. So I can use the distributive property to rewrite this as A minus lambda I times V is equal to the 0 vector. Essentially, I am factoring out this vector V. So one more time, what we're looking for is numbers lambda and vectors v, so that A minus lambda I v is going to be equal to 0. We already always have the solution v equals 0 is the solution. But we want to find non-zero solutions as well. So our options for solutions are 0 solutions. That doesn't happen. 1 solution. We want to avoid this. What's left is infinitely many solutions. Okay, so we are looking for the case where A minus lambda I has infinitely many solutions, and thus it is not invertible. A minus lambda IV equals 0. This happens if we have a free variable, and having a free variable will mean that we can't be invertible. Okay, it is really helpful if we know that our matrix is not invertible, or if we're looking for the lambda where this matrix is not invertible, to take the determinant. So we're going to set the determinant of this expression equal to 0. When it's equal to 0, then that means that we're going to have extra solutions to our equation, and we have that lambda is an eigenvalue. It turns out that this determinant is always going to be a polynomial, and we call it the characteristic polynomial of the matrix A. And it has some neat properties. Okay, so our goal now is just to find all lambda so that the determinant of A minus lambda I is equal to 0. These lambda are all eigenvalues. So let's do this with an example. We're going to find the eigenvalues for our example, and then we'll go back and find the eigenvectors.